All right, let us get started. Thank you to everyone for coming to this workshop today. Really excited to be showing you some of these tools. Most of the participants are on Zoom. We have one in-person attendant, so I'll be sort of going back and forth. This meeting is being recorded, so if you guys speak in the chat, it will be on the recording. So if you just don't want your face for any privacy reasons, you can just turn off your screen when you're asking any questions. So my name is Natalia. I'm the GIS TA for the UMass libraries. This is my first workshop of the year. I've been putting it together throughout the semester. I just want to get rid of, there we go. Goodbye. Is there a way to hide this?
Cover the top area of your screen, and then the more high loading meeting controls. Oh, you gotta get this hide. Quick escape.
All right, one sec.
It's hide video.
Hide video panel. As much as I want to see y'all. All right, cool. So this workshop is going to be sort of acting as an intro to QGIS if there are folks who have not used it before. Yeah, there's sort of an ongoing effort right now from the state of Massachusetts to try to include citizen science more, introduce members of the general public to it. So that's kind of what this workshop is about. So yeah, let's get started. So the overview of how this is going to go, we're going to do a brief sort of introduction to what citizen science is. We're going to go over how to download web data, citizen science data in the form of a CSV file, how to import a CSV into a map and convert them into points that you can see. And then the last part, we'll see how much we get through in the short time that we have. We're going to go over sort of a simple workflow for addressing sampling bias. And we're going to go over what sampling bias actually is and why it's important when considering citizen science data. And then if we have time at the end, we can sort of do a brief discussion of results. For those on Zoom, if you don't feel comfortable talking, you can also share your thoughts in the chat. Becky is going to be sort of like monitoring the Zoom room. I may not see questions or anything that pop up in the chat, but she'll, interrupt me if need be. So what is citizen science? It is the collection and analysis of data related to the natural world by members of the general public, typically as part of a collaborative project with professional scientists. Now, the landscape of citizen science has changed a lot with the introduction of smartphones into our lives. We have this ability, we have essentially this like GPS in our pocket, anyone with a modern smartphone. So we have this really cool ability to contribute to various citizen science projects. And so a lot of these are apps that you can download. A lot of them are free. On the right-hand side, I just have a couple of examples. We'll be using EDDMapS. EDDMapS specifically focuses on invasive species detection. So we'll be working with a couple of invasive species data sets for the state of Massachusetts. Some other ones included eBird, pretty self-explanatory. Loss of the night is really cool. You can essentially like take a photo of the night sky wherever you are, and it sort of tracks light pollution in the area. So that I think that's really cool. So there are all of these capabilities now with smartphones where like you can contribute data to these various projects. But with that, it introduces this problem of sampling bias. So relying on the public collection of data, it introduces this sort of inherent unevenness in the data collection itself. So examples of this include spatial bias, where there are large population centers or easy access to areas from roads or hiking trails, you're going to find a disproportional amount of observations in these places. Temporal bias could be another one, in which there are more observations made in the summer. That's just sort of an example I thought of. And a taxonomic bias. So if there are certain plants or animals that are either really easy to identify or, sort of have a kind of cultural importance, there may be kind of more observations made for these taxa over others that are maybe more difficult to detect, harder to find, or don't have the same sort of cultural importance. And so if you are conducting research that involves using citizen science data, if you're not addressing these sampling biases, you risk producing unreliable results. And we'll see some very real examples of this. So we're sort of going over a very simple method of how to address this in this workshop. So this is how sort of the overview of how it's going to work. We're going to be introducing what's called an effort proxy. Effort proxies can be lots of different things. They can be land cover, they can be population density. In this case, we're going to be using roads under the assumption that areas with more roads are probably going to have more people, therefore more observations. And so we're going to have to weigh our observations related to our road density. And so we're going to do that through kind of a combination of some simple QGIS tools and the field calculator to essentially produce a density distribution map. And the end result, we're going to have two observation density maps. We're going to have an uncorrected one and a corrected one. We're sort of going to compare back and forth between the two, notice any differences. And then we're sort of going to have a discussion on like, what are the limitations of this method? This is a very simplified method that will have some limitations, but I'm hoping that we can talk about that and sort of brainstorm, like, what would you do if you were utilizing citizen science data for your own research project? So let's go to EDDMapS, where I'm just sort of going to go over how to download data from these sites. So I think I'm already logged in. So this is something you guys don't have to do because once you download data, it actually takes a little while. It sends you an email after about 30 minutes. So you don't have to do this with me, but you can just follow along. So we'll go to species info. Let's say I want to look up a plant. Specifically, I want to look up an herb. Something that pops up in my mind is garlic mustard. That's a pretty common invasive species around here. So let's just click on that. You can navigate over here to points, and it will take you to sort of this interactive map where you can see basically the distribution of garlic mustard across the whole country. You can sort of estimate its range down here. It's sort of a temperate northern loving or northern US loving plant. I'm sure you've seen it around. So now if you want to download this data as a CSV, so it allows you to download as a shapefile as well, but for the purposes of this tutorial, I'm going to do a CSV. So to download a subset of the species records, click here. So we're going to follow this. And on the left-hand side here, it gives you a bunch of options to kind of narrow down your search. So we don't want Canada. I'm gonna do Massachusetts only. Massachusetts pops up right there. So now, as you can see, this map here has been updated just with points containing Massachusetts. So once you have your subset of data that you're looking for, you can click this CSV button again, and you will get this screen. You will receive an email shortly with instructions to download the requested content. So that's going to take a little while. And so because of that, I have prepared some data for you guys that you can use instead that I've already downloaded from EDDMapS. So if you want to follow along with this tutorial, now is where you are going to do some data downloads. But if you don't want to follow along, you absolutely can just kind of watch. But if you are downloading necessary data to follow along with this tutorial, type this link into a browser, tinyurl.com/EDDMapsData. And it's going to take you to a Google Drive folder where there's a subfolder called data, and we're going to go in there. So hopefully y'all have had enough time to copy this URL if you are following along. So I'm going to go over here now. Cool. So now we're in this Google Drive folder. You navigate to this data tab. So you have 3 different options for species that you want to look at. All of these are invasive species found pretty prevalently in Massachusetts. You can choose bittersweet, you can choose garlic mustard, you can choose Phragmites. You only need one. But then this file here, you're definitely going to need. So download this one. It's going to download as a zip folder that you're going to need to extract. And then make sure you save it in a place. What I would recommend doing is create a folder maybe on your desktop, call it EDDMapS data, and then put both your invasive species sightings CSV and your mass.roads into that folder. So I'll give folks a few seconds to do that if anyone's doing that. Yeah, okay, yeah, there's a request to explain what the different plants are. Bittersweet is a pretty nasty invasive vine that's found pretty much all throughout the state. It's particularly a problem because it's a vine, it sort of creeps up from the understory and can really strangle a lot of trees. If anyone visits the Connecticut River in Northampton, you'll see a lot of bittersweet kind of like choking out the maple trees that are right along the river. Particularly if you're going over the bridge that connects Hadley to Northampton, you'll see a lot of bittersweet kind of choking out the trees there. Garlic mustard is an herb. It's edible. So actually one of my favorite springtime activities is to go and collect the garlic mustard and saute it into a little thing. If you harvest it before it flowers, that's the best. But garlic mustard is a bad one. You can, Google an image of it and I'm sure you will have seen it. And then Phragmites is a wetland species. It's a grass. So in a lot of areas where there used to be an abundance of cattails, you now have this Phragmites grass. It's a tall grass. It's emergent, so it grows from the water, and it kind of has this like bushy top to it. So it's pretty easy to spot, and it is truly everywhere. It's a big problem in wetlands. So on that positive note, so the rest of this tutorial is going to be utilizing QGIS. So if you have QGIS already installed on your computer, you can just open it up. I'm sharing my Google Slides still. All right, let's fix that. All right, rectified. Fantastic. Okay, so QGIS, for anyone who has never used it before, kind of has a similar layout to ArcGIS, but there are some fundamental differences. You'll see that there's no base map when you open this. So if you want to add a base map, that's pretty simple. So that would be, you navigate over to this plugins tab. You click manage and install plugins. And this pop-up screen will open. You're going to want to search up Quick Map Services. I already have it installed, but if you don't, you can just click that. You click, well, I don't want to reinstall it, but this would say install plugin. Should be very quick. And then if you go over to web, Quick Map Services will appear right here. And so then, well, this has a lot of other options that don't come with Quick Map Services, but I think the ones that do, OSM, OpenStreetMaps. So let's just say, let's see, the Esri ones. Let's do light gray. It's pretty simple. So now you have a base map. Not super necessary to have a base map, but if you want it just for context, it's a good thing to have. So now we'll go over and add our data. So in order to add a directory, you can go up here to favorites, right click it, and click add a directory. And then you can set your directory to wherever you stored your data that you just downloaded. So I've already done that here. This is where I'm keeping my data. So once you've established that directory, you can expand these folders. This mass.roads you should have, and then you should also have a CSV of whatever invasive species you're working with. There are a couple of extras in here from when I was experimenting with designing this workshop. But mass.roads and your invasive species CSV are the only ones that you'll need. So first, let's go to mass.roads. You should only have major roads. I have all types of roads here, but if you downloaded a folder from that Google Drive link earlier, you should only see major roads. Now, that is one limitation with this. And it's going to ask for a geographic transformation. You can keep it the same. Just select this first one, click OK. And now the map has been populated with Massachusetts roads. What was I saying earlier? Oh yeah, so if you were to do a more robust analysis, you would use not only all roads in the state, but you would also probably use hiking trails. I was workshopping that and it really slowed down the processing power of Q. So for the purposes of time, we're only going to be doing this with major roads. So we have one component uploaded already. So the next thing we're going to do is add our CSV data. And so the way that we're going to do this is go up here to layer. going to navigate to add layer, and then add delimited text layer. I'm going to click on that, and we're going to navigate to our file. So mine is in here. It's going to be called mappings. That's going to be the same for all of your data. So let's open that. It's going to define the geometry. So X field is longitude, Y field is latitude. These are all fields that are contained within the CSV right here, as you can see. So any spatial CSV that you download from one of these citizen science sites is going to have latitude and longitude. Hopefully you don't have to do any unit conversions. So we're going to leave everything as is, and we're going to click add. What's up, Becky?
Remind the geometry CRS that it's valid. But point out that you might need to change geometry CRS.
Okay. Yeah. You might need to change geometry CRS if the, what is it, projection is invalid. Okay. Okay. But I think in this case, we're okay. And as you can see, all the points show up. So a couple of things to note here. You may notice that there are a couple of different kind of hotspots of observation points, one of them being in the Boston area too. But then there are also a ton in Westfield, which is kind of interesting. You know, you would think they're, you know, lower population. Why are there all these points here? The reason is that there is an interest group who is working on identifying invasive species in the Westfield watershed. And so if you right click over here in mappings and open attribute table, does that pop up in, okay, cool. Oh, it doesn't show up, the attribute table. Well, that's, yeah. Let's see. Okay. Well, I can do that. I don't think so. Sorry, y'all, we're troubleshooting. I can just do this. I'm just gonna have to do it a lot. Yeah. Okay. Okay, cool. So now we're in the attribute table. Sorry, we're working with limited technological services here, but you can see reporter, you can see the different people who reported these. You know, there's a lot from the Appalachian National Scenic Trail that may explain the ones that you see in Western Massachusetts. And then there's this, the Western Invasive Species Partnership. So if you X out of that, and then go back to this screen here, that kind of explains a lot of these points here in the Westfield watershed. So that's always something to keep in mind when you're working with citizen science data, is you have to be aware of, like, are there certain interest groups who are already focusing on the subject, and is that sort of going to affect the distribution of the points? And in this case, yes, there is an interest group who is recording sightings of garlic mustard pretty far off from the roads. And I'm very familiar with this area. It's quite rural, so people are quite literally like walking through the woods to find these. You know, there's a crap ton right here. So that's just something to keep in mind. So what we're going to do for the remainder of this tutorial is let's kind of undergo a simple method of addressing this sampling bias that we see here, where we have a disproportionate amount of points taken in the urban areas, almost, you know, very, very, very little in this area. Yeah, and so we're gonna see how it goes. We're gonna get as far as we can, and then we'll talk about it. All right. So the first thing we're gonna do, and this is something that's like a pretty common first step in a lot of the kind of papers and literature that I was reading in trying to drive this methodology, is that you want to normalize your observations to, usually it's a grid. So that's what we're gonna do. And there's a nifty little tool. Oh, and by the way, if you want to be able to see the toolbox here, that is processing toolbox. That just made it go away. But if you go up to processing and click toolbox again, then all of your tools appear right here. So we're going to search up the tool in the search bar. We're going to say create grid. It's very self-explanatory. It creates a grid. Do you see this pop up in the Zoom? Okay, wonderful. So our grid type is going to be a rectangle. The extent basically just refers to sort of the boundaries of the grid. And we're going to click that down arrow, calculate from layer. We're going to use our major roads as our extent reference. Horizontal and vertical spacing, we're going to make 5,000 meters. As you can see, it defaults to meters automatically, but you can change that very easily. So now a note on QGIS, and sort of one of the things that sets it apart from ArcGIS is that when you create a layer, unless you specify a file path for it to be saved to, it will only be created as a temporary layer.
It also changes CRS.
Change the CRS. Yeah, to pseudo Mercator. It doesn't have NAT83. What do you think? Okay. 26986, because we want to have consistency in our projections. All right, let's do that. Okay, so I didn't, let's see. So going back to parameters from before, if you wanted to specify a file path, you would just click this button here, save to file, and then you can save it to whatever directory you would like. But for this tutorial, I don't necessarily need to save this, so I will just, I believe it already created actually. Oh, look at our grid. It is a little wonky looking, but I guess that's what happens. So let's put this underneath right here. So we have our roads and our observations, and then this grid here. The color scheme's a little ugly, but I promise we'll change that in a little while. So the next thing we want to do is we want to count the number of points within each grid cell. And there's another tool that's quite self-explanatory that does that. And the name of that is count points in polygon. It pops up right here. And that does exactly what it says it does. Our polygon is going to be our grid. Our points are going to be our mappings layer. And it's going to essentially create a new grid with this additional field called num points. So let's run that. And it's going to take a second. All right. At this point, if anyone has questions.
CRS is the bottom report is the first here. If you wanted to change that, make the grid look straight.
Okay. CRS, bottom right. Change it to that. Okay. Oh my gosh. Why can I not? This is so silly. Why can't I see the bottom? Okay, one sec. Okay, well, that finished. Now let's try this again. There should be a little apply button. Oh my God. I can like do. Yeah, I just can't drag it up. Okay. If y'all are okay with working with a wonky grid, we can certainly do that. Okay. So this new grid has just been made. We can get rid of the old one. We don't need it anymore. And let's put this underneath again, just for viewing's sake. Okay. So now we're going to open up the attribute table, and this might be another thing where I have to stop sharing. Is that the case? Okay, I have to stop sharing and share this again. Sorry, y'all. It's going to be a bit of a back and forth here. All right. So now we're in our field calculator, or sorry, in our attribute table. You can see each grid cell's geographic extent right there. And our num points field has been added. So a lot of them are going to be zeros, but then, you know, because it's observations per grid cell and we have pretty small grid cell, but you can see there's some numbers there. Yeah. Oh, 16. So there's a lot there. Yeah. So that has our observations per grid cell. So now we're going to use the field calculator, which is a pretty common tool that you'll be using a lot of the time. So in order to do that, navigating over this pencil symbol, that toggles the editing mode. So as you can see, with the toggle editing mode off, a lot of these options here are grayed out. But when you toggle editing on, you can now have a bunch of options for working with this data. So we're going to go over to this little symbol here. This is the field calculator. So now what we're going to do is calculate the area of each grid cell in square kilometers. So right now the area is automatically saved in meters, but we would prefer to work with kilometers so they're not such big numbers. So we're going to call this output field grid area KM2. We're going to keep this as a whole number integer rather than a decimal number, because we expect that all of these are going to be 25 because, as you recall, we did a 5,000 by 5,000 meter grid cell. So the expression here is a $ area, which is already automatically calculated when the layer is created. Then division symbol, 1,000,000, 6 zeros. We're going to hit OK. So now all of these values are 25. That's what we expect. That's great. So now we're going to do a second field calculator expression. We're going to call this observation density, or obsdense, just as a little shorthand. Now we're going to change it to a decimal number. It's a little bit arbitrary how many decimal points you set it, but I'll just keep it at 3. And so now the expression here, you want to do an open quote because now you're specifying a layer name, num points, close quotation, division symbol, open quote, grid area KM2, which is the layer that we just made. So this is the number of points per 25 square kilometer grid cell. You're going to click OK. And that has created an observation density layer. So as you can see, a lot of them are going to be zeros because they're 0 points, but then some of them start to become populated. So let's visualize this. So I'm going to toggle off editing, save my changes, share my screen again, back here. All right, so let's go over to count. So in order to edit the symbology, you right click, navigate over here to properties. We're already on the symbology tab right here. We're going to, instead of single symbol, we're going to do graduated colors. It automatically defaults to red. And for our value, let's do our observation density. And mode down here, we're going to change to natural breaks. And I'm going to do 10 classes because it will look a little bit better. So we have an observation density map. Now, I really don't like those grid cells. I don't want them anymore. So we're going to go back to properties and get rid of the grid lines. And so the way that that happens is you navigate over here to symbol, click this down arrow, configure symbol. You go down here to simple fill. Stroke color, we're going to hit that, and we're going to select transparent stroke. And that is going to basically make the boundaries transparent. Let's see what that looks like. Okay, better, but I don't want to see the white space anymore. So we're going to go back to properties. We're going to click this symbol here, right click, change opacity, and change opacity to 0. So now if we turn off our roads and our mappings, you have yourself a nice little pixelated density map. So you could stop here, right? But the whole point of this workshop is to address sampling bias. So we're going to keep going, and y'all are going to have to deal with it. All right. So now that we have created this grid, our area of focus is going to shift a little bit to our effort proxy, which, as I said earlier, is going to be our roads. So the way that this calculation is going to happen is we're going to use essentially a proportion of roads per grid cell. But right now our roads layer is a line shapefile rather than a polygon. So we're going to have to convert it so that rather than just having a length attribute, it also has an area attribute. And so the way that we're going to do this is with the buffer tool. Yeah, and in that Google Drive folder, there's sort of written instructions for you guys to follow along. There is a slight amendment I'm going to make to those, which is that the instructions specify 100 meter buffer distance. I was doing some experimenting and I decided that 250 would be more effective for sort of visually displaying this. So we're going to do 250 meter buffer. Our input layer is going to be our major roads. And you want to make sure you check this box here, dissolve result, so that rather than having a bunch of different overlapping buffers, you actually just have one single polygon. And this is going to take a little while to run, so just going to let that do its thing. And it always stops exactly at 99. It's like really just messing with me. Yeah.
What are the formulas we put in the field?
Great question. Okay, let me let me do that right now. Look, our buffer. Okay, let's go back here. Yeah, okay, yeah. Let's so yeah, you guys can actually you can find all of these calculations. I'm gonna go back to the back here. If you go to this link where we originally download data, in workshop materials, this document, Working with Citizen Science Data, this has all written instructions, including all of the calculations. So the first calculation we did was deriving the area of each grid cell in square kilometers. And so this is the formula for that. So $area over 1 million. And then the second expression that we did is this one right here. So it's the num points, which we derive from the count points in polygon tool, divided by our grid area, which we got before. Yeah, thank you for that question. Sorry, I didn't specify that all of these equations exist somewhere. All right, let's go back to Q. So we have our buffer. As you can see, all of our roads have created a 250-meter buffer associated with them. You don't need the roads anymore. And now it's not going to load. We love that. Okay, there we go. So the next thing we want to do is basically perform a function that will, I feel like clip is the wrong word, but extract our road buffers to within each grid cell. I don't really have a better way to explain that, but you'll see when I visualize it. So we're going to, find the areas where the road buffers intersect with grid cells. So this is going to be the intersect tool. Intersection, sorry. So that's going to create this pop-up. So the input layer is going to be our count. You can, actually, before I do this, I just want to rename this because it's going to get confusing. QGIS a lot of times just kind of automatically generates names. And so you have to, be careful if you're working with a lot of layers so you don't get confused. I'm going to call this grid with count, which is what it is called in the little tutorial document. Grid with counts. Okay. Just so that's clear, it's important to be specific about your naming conventions. All right, our input layer is grid with counts. Our overlay layer is our road buffer, which is just called buffered. You can also rename this to road buffer if it'll be easier to remember. And we're gonna run that real quick, and this will also take a second. All right. Hopefully everyone's following along. So I guess I should take this opportunity to explain that the purpose of this is to eventually be able to derive a road proportion per grid cell, or rather road buffer proportion per grid cell. And the buffer that I chose, 250, is somewhat arbitrary. It doesn't actually have to do with the sort of effort of walking 250 meters away from a road. It's more of how do we sort of, how do I get sort of a road proportion that accurately displays the changes that we're making without sort of making too drastic of a change. Because if we do a really wide buffer, say like 1,000 meters instead of 250, it's going to much more drastically change our observation densities. Is there a chat question? Let's see.
Remember, these people being recorded, so that they can watch again.
Cool. Yeah, and a reminder that this is being recorded so that y'all can watch again later if you need to, because this is a lot of information being thrown at you in an hour. And while this is running, I'm going to grab my computer charger because I just realized I did not set that up. Yeah, really? So Becky's both managing the Zoom room and following along with this tutorial, so kudos to her. All right, cool. So that happened. Let's turn off this buffered layer. So this essentially created what looks similar to a buffer layer, but you may be able to tell that they are now split by the extent of the grids within the grid cell. So yeah. Okay.
What is the field type for non-points divided by grid area?
Okay, good question. Yeah, you're gonna want to do decimal, which is the second option in the dropdown. And you can specify the number of decimal places you want. I just left it at 3. Yeah, I would say leave it at 3. But yeah, you want decimals. You want to make sure you're not doing whole numbers because that's gonna really skew it.
I added it to the.
Yay. Okay, thank you. Cool. Becky's also actively editing the tutorial, so yeah, she gets #1 prize in multitasking. Anyway, so we have our intersection that is like split by our grid cells. Yes.
Not really good. Could you give a quick, like, what is the purpose of this map?
Okay. All right. The purpose of this map is to sort of like place an eye of critique over sort of citizen science observation points to essentially not take them at face value. So okay, so I'll just show them again. We have all these points, right? This is a distribution of garlic mustard in the state of Massachusetts as observed by folks using EDDMapS. So all of these are species recordings in EDDMapS. You'll notice that there is a pretty high density of points in the Boston area and also a really high density of points in the Westfield watershed. Now, you could take this at face value and say, oh, there's probably no garlic mustard in southern Massachusetts, but that's actually probably not true. So this is sort of a workflow that addresses sampling bias in the form of population density and proximity to roads or access via roads, in which we're sort of performing a correction that changes the weight of point observations in like highly road dense areas. That's what you're doing. There's a document. I'll just. So yeah, explanation of sampling bias. That's what we're doing. Sorry, I'm just gonna go back here. If you navigate to this URL right here, tinyurl.com/E EDDMapS data, it's going to take you to a folder that has written instructions for how to do all of this. So if you want to follow along, you can, or if you want to just like save that document and try this out yourself later, you're totally welcome to. Yeah, but we're making really good time. So yeah, I think I'm gonna keep going, I think. Yeah. We're doing great. Yeah, okay, yeah, no, that's great. That's a great idea. Thank you, Becky. So I want to turn on our grids with counts. So we derived an observation density. So we started off with these points. We created a, oh, sorry. Do I have a grid? Yeah, we created a grid. We calculated the number of points in each grid cell. And then we did a field calculator expression that was the number of points over the area in square kilometers in order to get an observation density map. And it looks like this. So the output of this is going to be a second observation density map that is corrected to our effort proxy. And then we're going to sort of compare back and forth. And you're going to see there are some differences. Okay, cool. Okay, so I was at intersection. That's where we were at. Sorry, I just gotta get my head back in. Okay, let's go to the attribute table for intersection, and I'm gonna have to do the thing again where I stop sharing and then I start sharing again because reasons, technology. Okay, this is the attribute table for the intersection layer that we just created. You can see our num points are there. Our num points, grid area, kilometer squared, and observation density. These are the 3 fields that we created earlier. And we also, so we're going to add a couple new fields. So again, to do that, you click this little pencil button to toggle the editing mode. Navigate over here to the field calculator. And this output field name is going to be buffer area. in square kilometers, because we want to calculate the square kilometer area of each sort of grid cell's road buffer, if that makes sense. You want to change the data type to a decimal. I'll just keep it at 3. And this is going to be a duplicate of the expression we did earlier. So it's going to be $area, division symbol 1 million. So that's converting square meters to square kilometers. We're going to click OK. And that created a new field. So I think I wanted to do, we may not have to join to our original grid actually, because all of that information is here. Sorry, I'm just like having a thought. Let's see if we can do this without the next step. So step 10, if anyone's following along with the document, is add the area of each intersection back to the grid cells. I actually don't think we have to do that. So I'm making a last minute change to see if it works without doing that. Oh, no, yeah, you're right. Okay. Thank you, Becky. Yeah. Okay. So we actually do want to perform step 10 because we want our results to be displayed as a grid and not as our road buffer. So I'm gonna exit out of there, do the thing again. Okay, so we're gonna use a new tool now. Is join attributes by location is the name of the tool. And I like using the search bar. I usually don't go through and like click through the toolboxes. I just find it to be quicker if I already know the name of the tool I'm looking for. So this is going to join our intersection layer to our grid layer. And the way that that's going to happen is we're going to join by location to features in our grids with counts, which we created earlier, by comparing to our intersection. I'm gonna leave everything else the same. Intersect is checked. That's what we want. And we're gonna run that. And that creates a new grid, which is good because we're gonna need the grid in order to visualize it. So yeah, thanks for that. I forgot about that. Looks a little wonky, but we will fix it in a little while. So let's look at this attribute table again. So you'll see we have our original fields from our original grid area, these 3 that we made. And there are going to be some duplicates too. You don't really have to pay attention to those. That just kind of happens when we perform the join. And then we have our buffer area. So what we're going to do now is calculate a road proportion. So we're going to turn on editing mode again, field calculator again. We're going to call this output field road proportion. You can shorthand it to whatever you're going to remember. And so then the expression for this, you want to do open quotes, buffer area KM2, which is what we calculated earlier, division sign, grid area KM2. So this is taking the road buffer area divided by the grid area in order to give us a proportion of each, the proportion of roads in each grid cell. And you'll see like in the urban areas where there are more roads, it's going to be much higher. So let's click OK. That calculated our new road proportions. In a lot of areas, they're going to be quite small in the areas where there are fewer roads. So this is our effort proxy, this here. This is what we're going to be applying into our next calculation that is going to give us an effort adjusted observation density. And that's going to be the last calculation we do. And then we're going to visualize our results and sort of like talk about what we're seeing. So let's go back into field calculator. I'm going to call this observation density adjust because it is our adjusted observation density. So this is going to be the most complicated calculation here, but I'll explain everything. So open quote num points, which is the number of points per grid cell, minus, now we're going to have a parenthesis, open quotation, num points again, close quote, times, open quote, road proportion. And then you want to make sure there's a close quotation and you close the parentheses. Now, if it's an invalid expression, it's not going to let you run it. So the OK button is grayed out. But once you complete the expression and it's valid, it's going to let you run it. So an explanation of what this is. So we have our original number of points, but now we also have this road proportion in here. And so what this expression is essentially saying is that we are going to be weighing the points that are in areas with heavy road density. We're going to be weighing them a little bit less. So that's essentially what this means. Yeah, if you have like more questions about that, feel free to ask them in the chat, but it's essentially the areas with fewer roads are going to more or less stay in the same place, like weight-wise, and then sort of comparatively, the points in or urban areas with a lot of roads are sort of going to be weighed down a little bit. So that is what that is saying. So we now have our effort adjusted observation density. So real quick, I'm just going to close out of that. Go back here. I'm going to right click here. I'm going to toggle editing. That's going to turn editing off. I'm going to save that. I may as well just do that for all of them. So I'm going to duplicate this layer because what we're actually going to, well, actually, no, we have our original observation density, so I'm not going to duplicate it. But what I'm going to do instead, I'm going to go to properties. I'm going to rename this layer observation density adjust. And grids with counts, I'm just going to rename it observation density. So we can kind of toggle between the two, see how they're different. Okay. I don't need this anymore. I really just need observation density adjusted and observation density. So we're going to go and edit the symbology here to make it similar to the first observation density. To recap, you go down here to symbology. You go down here to graduated colors. It automatically does white to red, but you can change that if you have a preference. So now this is our observation density adjusted. So our value is going to be observation density adjusted. Rather than equal counts, we're going to go down here to natural breaks. Oh, and this is probably a good opportunity to say, like, there are lots of options for how you can sort of like display the distribution of values. And that's going to obviously influence how people interpret these maps. So for the purposes of this tutorial, to really get a good sense of what the difference is between our adjusted observation density and our original observation density, I'm going to do this one, natural breaks, because in my opinion, it displays the data pretty well. So we're going to do 10 classes. And I want to get rid of that. I want to get rid of the grid lines. So you go over here to symbol, click this down arrow, configure symbol, go down here to simple fill, and the stroke color is going to be transparent. Click OK. And then the other thing we want to do is toggle the opacity. So we're going to right click on this top symbol here, which is just 0. Change opacity to 0, and then click OK. So let's see what we're working with here. So this is our observation density. This is our adjusted observation density. And this is our original observation density. I'm just going to try to get a good view here and sort of switch back and forth between the two. So this is effort adjusted, regular. Effort adjusted, regular. Effort adjusted, and regular. So hopefully you guys are noticing some things here. Hopefully you're noticing that over here in Boston, all of a sudden, all of these points have a much lower weight to them. That's probably where I see the biggest difference. Now, on the other hand, over here in sort of like the Westfield area, that weight kind of stays the same. And if you recall from our roads, the road density here is very sparse. So the weight of these points did not change that much. Let's turn this back off. But then all of these points here sort of on the, the periphery of the Westfield watershed also experienced some change. They actually reduced a little bit. So down here we have Springfield. So the Springfield points reduced. So we're in the adjusted, non-adjusted, adjusted, non-adjusted. So that's essentially the output of this workshop, you have a density map that has been sort of adjusted by our defined effort proxy, which was our roads. And as I mentioned, this is like a very imperfect methodology. So I think what I want to do now is have a bit of a discussion on like what are like the pitfalls of this method? What would you add to this method if you had more time? And assuming that, we're not sort of confined to this hour-long chunk of time in order to have this, to sort of undergo this process. So I'm going to stop sharing the screen, kind of open it up to the chat or to, folks in the room. Like, what would you change about this? And I have sort of some thoughts of my own. So if like no one has thoughts, I can share some of my thoughts as well.
About hiking trails and like what happened when you guys.
Yeah. Okay. Well, okay. So one thing is, you notice we only use roads, major roads. Sorry, we only use major roads. I wanted to use all roads in the state, because I thought that would create a more accurate result. But then the processing speed of QGIS, it got really, really slow when I was doing the buffer. So I opted to only do major roads, but something that would really improve this method is if you did major and minor roads, and if you also did hiking trails. And I know this from personal experience for myself when I'm kind of collecting, data for various citizen science projects, is that like a lot of times I do it on a hike. That's actually like that's the most often that I'm going out and collecting this type of data. So hiking trails would be really important to include if you were to do this yourself in the future. The other thing is land cover. So we didn't discuss land cover in this tutorial, but if you are looking to essentially predict where you might find a species based on current observations, but you're sort of trying to interpolate where there might be observations that haven't been recorded, land cover would be a go-to layer, where if you sort of have a distribution in a certain land cover, you can find other areas with that same land cover and essentially say like, okay, there's a likelihood that this plant can be found here. And then there are other sort of geologic aspects and topographic aspects that you might want to look at, stuff like hillshade, slope direction can really influence soil types. Yeah, thank you for mentioning that. Soil types and acidity. Yeah, you guys are thinking of like all the right things. Yeah, so if you like have a deeper familiarity with the species that you're working with, there are lots and lots of different layers. Population density, awesome. Yeah, this is exactly what I wanted to. Yeah, this is great. So our roads are sort of like kind of a proxy of population density, but you could really improve this method by actually looking at population density statistics. I believe the census, you could get that from the census, potentially. Yeah, you can get population density from the census, and then you can probably figure out like how many points, per population density. Yeah, you can do like a much like deeper level analysis of this than what we just did. Am I missing any others? Like what else would one use? Precipitation, if you're looking at a larger area. And something that you'll notice on the websites, I kind of want to go back to EDDMapS since we have a couple minutes. Let's go back. Maps. Let's go look at a garlic mustard map, because I just want to kind of demonstrate how, oh my gosh, why aren't you typing? A lot of times when you see, oh, no, I want to do states. Actually, no, let's do counties. A lot of times when you see points distributed or observations distributed, you'll see them done by county. And so this is basically to avoid the issue that we ran into, is when you're analyzing sort of a smaller area, there's a lot more uncertainty that's introduced. So, but if you're just kind of looking to get a general species range, a lot of times you'll see this kind of binary map that's like, was it cited in this county? Yes. If yes, it's going to be green. If there are no sightings in a county, it's going to be white. And so a lot of times if you're doing sort of like wider analysis over a larger land area, you're going to see these really kind of highly simplified data maps, which is like simply showing like an estimated distribution. And this is garlic mustard, it's very possible that there is, garlic mustard in like southeastern Georgia. And so that would really kind of influence what we understand its range to be. I mean, I would say it's quite likely, but you have kind of like lower populations down here. Like other things influence the data collection if there are sort of like public incentives or public programs that are doing education on the distribution or on how to collect this data that can really have an effect. Yeah, but then obviously once you start working with a smaller area, then you start, encountering these sampling biases a lot more. And so kind of like the smaller your area, the more you have to consider all of these factors. And as you saw with the our point distribution map, there are just like a lot of points out here. And that's because there is like a specific group that is going out here and collecting data in the Westfield watershed. Like my favorite part is this right here. Like there's just like one person probably just went through and like just did all of these. So what I'm looking at here is probably much more accurate to like what the garlic mustard density probably actually is, but because we have this like concerted effort to go and collect point data here, and then like not so much over here, it's all about telling a story, really. And the story that this tells may not be the story of what's actually there. And that's sort of the that's sort of the like bit of like wisdom I would like to sort of impart with this workshop, is to say like if you have this data, like don't necessarily take it at face value. So yeah, I think that's all I have for y'all. If you have any questions, feel free to drop them in the chat. I'll stick around for a few minutes, but oh, are there more? Yeah, no, there are more slides, but it's essentially like what I was talking about. How can this be improved? Okay, I listed some here. Include minor roads and walking trails. Include this one we didn't talk about. Include analysis of point distance from roads. So you can like rasterize, you can create a distance raster using the roads, assign a value to each of the points, and essentially say points with higher values, aka farther distances from roads, they're going to require more effort and are therefore going to be weighed higher. So that's another thought. And then land cover analysis, and then folks in the chat made some really great suggestions for soil type, acidity, hill, sort of like slope aspect and slope direction. Yeah, lots of different things to be improved with this. And actually, yeah, so the last thing I want to share is this upcoming event is this is the City Nature Challenge for Western Mass. So this is a direct opportunity for you guys to engage with citizen science. What? Oh, am I not sharing? Oh my Lord. We're doing great. We're doing great. Yeah, I just want to plug this event right here. There it is. Join people around the world observing wildlife. This is coming up. It's like 10 days from now. So now you guys have some tools and understandings of citizen science. So now you can participate in a really direct way. So scan the QR code here to learn more. There's also a link right here. This is being offered through CNS, it looks like, the College of, CNC. City Nature Challenge. This is City Nature Challenge. Okay, cool. Yeah, I think that's all I got. Sorry, I lied before that there was actually more, but now I'm done. Thank you for being here. All right, yeah, thanks y'all. Yeah. Thank you, everyone. Have a good rest of your week.
Yeah, that was very interesting.